So Victor's presentation will be towards a lower footprint readout of persistent current states in fluxonium qubits. Over to you, Victor.
Yeah, so I mean, a bit of an apology because I did change the title from what it was originally, but I believe this is more precise. So if you've been in some of the other talks, especially on Monday, I believe, you already know what this towards here means, so it's kind of a work in progress. Yeah, so I believe most of you have been in Lorenzo's talk, which was 5 minutes ago. So if you've been there, you've already heard things about how we want to have this fluxonium as an operating platform for coherent analog quantum computing based on superconducting devices. Also, you may have heard about this on Andrea's talk on Monday, or also there was a workshop during Sunday, which I believe also talked about this. So I will not go too deep into this, but I will to give a couple of sketches. So as we just said in Lorenzo's talk, when the external flux in the fluxonium loop is at half-flux quanta, you have this solvable potential, and it's characterized by these two current states. Yeah, it's characterized by these two, like the ground and excited state, having two wave functions where one is symmetric and the other one is asymmetric in the other world. And when this happens, well, also notice that you have the other energy levels are super high up. So this means that you have a highly anharmonic system. And we say it's anharmonic because we compare the separation in the energy levels with respect to a harmonic oscillator, which would be equally spaced, which here it isn't. When this happens, for this two-wall potential, we have this left and right circulating currents clockwise and anti-clockwise at half phi naught. And why is this important? Well, when you run many algorithms rely on this persistent current basis. So when you want to run an algorithm in your quantum computer, you encode your problem as a Hamiltonian that then you write in terms of, you try to represent in terms of this persistent current basis. So obviously, when you finish running this algorithm, you want to read out this persistent current basis, and that's what we are here for. So we want to read out in the persistent current basis. So of course, if you know about this, you probably know that this is not something very new at all. In fact, there's this paper on the superconducting persistent current qubit, which also works in the persistent current basis mainly, and it's from a long time ago, from 1999. And it's from Orlando, Moish, and other people. So just a small note on this. This is on persistent current qubits, which are 3 Josephson qubits. They're also known as 3 Josephson qubits. And what we're working with is fluxoniums. So although they have many similarities, fluxonium, we work in the persistent current basis as a persistent current qubit because it's the same basis. They are a bit different. And actually, for the fluxonium, it has much smaller energy scales generally and smaller currents as well. So for the outline, first I'll go through a recap on the fluxonium yet again. Then I will explain regular readout for qubits. So this is the dispersive shift readout. And then I'll explain the Whitwell readout, which is the main topic for this talk. And then I'll finish with some future work on things that we're doing along the same lines. So okay, back to the fluxonium. So again, fluxonium, we have the Josephson junction, we have a capacitor, and we have an inductor. And the associated energies with this are the Josephson energy, the charging energy, and the inductive energy. Then we also have this variable, beta, which is the ratio of the Josephson to the inductive energy of the qubit. And this beta is actually proportional to the height of this solvable potential, that barrier that separates the two wells. Then the Hamiltonian of fluxonium looks like this. Again, we've already seen this in previous talk, but well, we have a term for a charge operator. You have a term for phase due to the inductor. Then you also have a Josephson energy term, which is related to the Josephson junction. And actually, the potential, it's related to these two terms, the phase, so the inductor and the Josephson junction. So you can imagine this quadratic term as giving you the parabolic shape of the potential, and then the Josephson energy term, which has a cosine, you can imagine it as adding a cosine in top of this parabola. So you've also noticed that we have this external flux. So if you were in superconducting physics 101 back in your bachelor, you probably heard that when you have a magnetic flux threading a superconducting loop, this induces some persistent currents. So what we can do is by controlling the external flux threading the fluxonium loop, we can tilt the potential because, as we said before, the potential energy is just like these two terms. So if we change this external flux, we'll be adding a phase to this term. So the cosine, the term that we are adding on top of the parabola, will be shifting in phase. But if we shift all the way to 0 phi naught, we get to this different fluxonium regime, which, although it's very interesting, it's not what we're really interested in because it has some other properties. So generally, we don't want to tilt past, say, 0.2 phi naught. So just from the way to like half flux quanta to 0.2 more or less. So what we can also do is we can add some more tunability to the fluxonium, and we do this by adding an extra junction. And then the potential looks like this, the Hamiltonian, where we have these two terms of alpha that account for the asymmetry in the junction. And this is often due to like fabrication errors and something. If we set these alphas to 1 and we do some trigonometric tricks, we can write the Hamiltonian as this, where we have the phi x term that's tuning, it's basically changing the energy. So you can write the Josephson energy in terms of only phi x. And essentially what this means is that you have this loop acts like a tunable junction. And it's a tunable junction, therefore, when you thread flux through this loop, you can control the height of the barrier, which, remember, it's proportional to this EJ over EL. So you can tune all the way from the highest barrier at double well to single well potential. And just a note, well, because this is a conference about quantum annealing, so you've noticed probably that we call this flux phi z and this flux phi x. So this is related to the fact that when you're around phi z at the sweet spot, if you have an Ising Hamiltonian, then you can more or less understand this. Well, you can actually control to some very good approximation the sigma z coefficient with phi z and the sigma x coefficient, Pauli coefficient with phi x. So this is it for the tunability range of the fluxonium. Just remember, we can tune the tilt with phi z and the barrier with phi x. This is also interesting that when you tune all the way to single well, you have a harmonic oscillator-like energy. So if you work in the persistent current basis, then when you tilt, if you go from the sweet spot to somewhere else, you can pretty much determine with this tunability, you can make the ground state be one or another, depending on which way you're tilting, so left or right. And with a barrier, you can also control this transition probability from one persistent current state to the other. So now we're interested in reading this out. And for this, first I have to explain how normal readout usually works in superconducting qubits. So for readout, it's kind of a dilemma because what you want is you have a qubit and you want to measure a difference in the energy of the qubit. To measure this difference in energy, you have to couple it to the outside because you want to measure it. But this will add, essentially, you will not have anymore like this nice closed system where the qubit is well isolated and can be controlled and has like nice coherence times. So this is something that you have to do. And to solve this coupling problem, what you do is you couple a resonator to the qubit, so it acts like a mediator with the environment. And this, so this is something that you can do is, a resonator is just capacitance and an inductance in parallel. And if you look at the energy, it's just a harmonic oscillator energy. And then the transition from the ground to the excited state of the resonator, this is what we call the frequency of the resonator. So to couple it to the qubit, you just add this coupling capacitance, which effectively means that you're just putting the resonator and the qubit close together, because if you remember, a capacitor is just two parallel plate conducting plates. And well, here you have the abstract circuit for the qubit and the resonator, and here you have a physical circuit. So you have the same colors, so this is the qubit here, and you have the resonator, which is this elongated thing over here, which goes to a CPW, and then you have the coupling capacitance. So if you see, like here, you have this U shape in the resonator that's kind of like wrapping around the qubit's right-hand resonator. So generally what you want is, first, you don't want to put the resonator too close in frequency to the qubit, because if you do this, you have a hybridized system, and you don't want this because you want your qubit system to be an isolated system, which is not influenced by the resonator. And you also don't want to put this too close together, because then you have very strong coupling, and you have a strongly coupled system, and it has different dynamics than what we're interested in. So generally, you put the frequency of the resonator slightly far away from that of the qubit, and you also want to put this kind of bit further away, so it's weakly coupled. And in this regime, it's what we call the dispersive regime, and it essentially means that the frequency of the resonator can be seen as shifting a bit by this value chi, plus or minus chi, depending on whether you shift like up and down. So if the qubit, say, it's in the first excited state, it will shift like plus chi, or if it's in the ground state, it will shift like minus chi. So the total shift is 2 chi, and yeah, you have this shift that's dependent on essentially the energy state of the qubit. So can we do this for persistent current? Well, no, but actually yes. So the thing is, if you think about what we just said, when you have this double potential, the dispersive shift, what it allows us to do is to check the difference in energy states of the qubit. But if you want to check this for the left and the right circulating current states, well, at the sweet spot at least, they have the same energy. So I mean, you cannot tell the difference in energy between the two of them. But you could say, okay, what if we tilt them a bit? So imagine that you have a small tilt, and now this is your left state, and this is your right state. You still have two problems. The first one is that because the tilt is very small, the dispersive shift that you will get from one model or another, while it's not exactly the same, it will be so similar that you will not be able to resolve the difference between one and the other. And even if you were able to do this, notice that when you're around this half-flux quanta, if you tilt one way or another, you have asymmetry. So if you tilt, say, this state and this state, if they have the same tilt but different ways, when you measure, you'll see the same dispersive shift due to one well being higher up than the other and the other well being higher up than the other. But as we said before, persistent current readout and, well, people operating with persistent current, I mean, this has been around for a while. So if you notice on Monday's talk from Dr. Lopasco, we also had a circuit similar to this one. So what you can do when you want to read out persistent current state is you couple a tunable resonator to the qubit. And this tunable resonator is just a resonator with a loop interrupted by a Jefferson junction. And what happens is that when you shift the changing current in the qubit will induce a shift in the flux of the resonator that will depend on the persistent current state of the qubit. So with this, then the frequency of the resonator will also change depending on the persistent current state. However, with fluxoniums, this is not so easy, because what we need for this is you need a relatively high current, which you can do with 3 Josephson qubits. But for a fluxonium, we have a much smaller current, so we are trying to do something else. And this is what gets us to the main topic of this talk, which is the Weitzwell readout. And this is like a different approach to this persistent current readout that relies, instead of on adding more elements like this tunable resonator, we just rely on having good control over our qubits to project the persistent current state of the qubit to a potential shape where this readout can actually be done via normal dispersive shift. And this is a method that was introduced by Chris Quintana in his PhD thesis at UCSB, and we are basically basing the research on this and expanding a bit on it. So remember that the problems that we had is that, well, dispersive shift that is induced by one shift in the upper well and the lower well, the two-well potential is very similar, and then this symmetry around half phi naught. So what we can do is the following. So suppose you finish an algorithm with, say, like a small barrier and a small tilt. So what you can do is, if you have control over this barrier and the tilt, you can just raise the barrier a lot. And what this does is it isolates the energy levels of the wells and the potential of the qubit. And then if the barrier is high enough, well, when the barrier goes to infinity, you have these two like being actually totally isolated, but of course the barrier cannot be infinite. But to a good approximation, for the lower levels in this well and in this well, you have an isolated system. So this allows you to then like tilt by a high amount to some point where the energy landscape of this well and this well are very different. And when this happens, because the dispersive shift is measured as these interactions between the energy levels of the qubit and the energy levels of the resonator, you will get a very different dispersive shift from this well and this well. By the way, this I'll call the upper well because it's higher up, and this lower well. But well, we solved the first problem, but we still have a problem with this symmetry. So, yeah. And yeah, and we measure the readout as the difference between the dispersive shift in the upper well and the lower well. So what happens if we tilt the other way? Well, actually, it turns out that we can still do the same because for most algorithms, when you the range of operation is around, say, like 50 or so milliphi naught away from the sweet spot. So it's a very small range. So if you find a region in phi z that's wide enough when you want to do this, if you tilt, you can still be sure that you'll be able to land in this region where you can do this kind of readout. So just to compare it with what we just explained. Usually when you do dispersive shift and you calculate it to an approximation, what you do is you compare the shifts that you get from interactions of the ground and first excited state of the qubit. What we do here instead is we want to measure the difference between two dispersive shifts instead of just like having only one dispersive shift. And this difference is given by the dispersive shift in the upper well and the dispersive shift in the lower well. And again, this is made possible because if we have a high enough barrier and a high enough tilt, then the energy landscapes. So it's not only that the ground state of the upper well and the ground state of the lower well have different energies, but also the energy spacing in each of the two wells will be different because they really are very different because we have this high tilt and they are very isolated. So then essentially the energy landscape here and here is different, and this is what gives us these two different dispersive shifts. So this is something we can simulate, and that's what we've done. We want the dispersive shift to be higher than the absolute value of the dispersive shift has to be higher than 2.5 kappa, where kappa is related to the width of this Lorentzian. So it's basically something that allows you to resolve the two Lorentzians from one another. And for a fluxonium here in a similar range as the ones we fabricated, we have a discern energy of 9.9, and we can see that we find this region around 0.25 and 0.3 phi naught. In some cases, we do not find this, and I'll go kind of faster about this. But what we can do then is, so here you have fluxonium of a discern energy of 19.9 gigahertz. What you can do then is, well, because you have tunability of the X loop, it not only tunes the barrier, but it also tunes the spacing between the energy levels of the qubit. So by changing phi X, we can change this spacing, and we can go to some region where before we had this, and now if we move phi X to around 0.35 phi naught, we can actually find a region where we do actually get this effective dispersive shift to be high enough that we can resolve it. Of course, we have to be careful because when we tune the barrier closer to half phi naught, we also get more interactions between the two wells in the double well. So at some point we cannot do this because we don't have this isolation anymore between the wells. Yeah, so for the future research, we are actually looking into combine this with some research by Jan Bob, who's right over there, on this sort of qubit that it's like a qubit and a resonator at the same time, kind of. So what we're doing is you have an internal resonant mode in the fluxonium that's a resonator-like mode, and you can use this for readout. So we try to find a parameter range via simulations that allows you to combine this double-well readout with this also common mode qubit. And we have fabricated devices to test this double-well readout as a standalone, and also another device to test, start testing both of these. These are fabricated, we have them in the lab, and soon hopefully we'll be measuring them and we'll have results, so stay tuned for that. And this is our lab, and this is our team. So if you have any questions.
Great, thank you very much, Victor. We have time for questions. Let me grab this. And I'll go straight to Shensai.
So are you saying at the sweet spot you cannot do the dispersive shift readout? This shift is too small? You have to move away from... So
for sure you can do normal dispersive shift readout, but you cannot do this double-well readout because the two wells are basically the same. So this effectively dispersive shift that we're trying to get, it's basically zero because you have the two wells being symmetric.
Can I say it a bit differently? You're trying to project...
Can we get the microphone if that's okay?
Maybe this helps. You're trying to project on a different basis. But you're not trying, if you do the standard dispersive readout at half flux, you're projecting on the qubit basis, which is a superposition of left and right. But you want to actually project on left or right.
That means you have to move out. Otherwise...
I will let you answer.
Okay. So, I mean, the thing is, you're trying to read out the persistent current, and dispersive shift measures difference in energy. So, in this case, when you're here, you have the same energy for the two persistent current bases, the left and the right. So, even if you measure, you will not see a difference from one and another. This is different than, so, because you could say, okay, no, when you do this, I mean, you have the same probability of both states, so you get like 50-50, so that's why you cannot tell. But this is different because what you would do is if you start your algorithm here, so you have like a superposition of these two, and you want to say like read out the persistent current basis, then you would do this, and you would tilt, and depending on whether you're here or here, you would read out and get one or the other. I don't know if.
I understand. Because in energy basis, it's flat. Flat means
yeah.
You have the current is zero.
I mean,
but the current is the tilt of the energy, and at the sweet spot,
it's zero. Yeah.
I mean, both are both.
Yeah, because the persistent current.
And then you have to move out. Then you have different current.
Yeah.
That's what you want to read.
Okay.
But does that cause decoherence?
You mean when you tilt?
Yeah, that's right. If you move out from the sweet spot.
I mean, at the sweet spot, it's where you usually have like higher T1. So if you have to be careful about this. Yeah. So we're still studying the dynamics, but you have to find like ranges of time or like how strong or fast your pulses have to be so that you are allowed to do this before like say you have like decay from here to here. The thing I did not mention is that this step here from when you tilt, it has to be non-adiabatic because, of course, if you're being adiabatic, you'll always stay in the ground state, so you will never have population here.
Any more questions for Victor? Or maybe I can ask a quick question then. So. You had a citation to the Waterloo or Northrop Grumman or something. Can you go back? You were showing that a second ago. Yeah, this. So the problem for your setup is that you're persistent current is too small to be able to use this technique. Have I understood that correctly?
I mean, that's one thing. I guess there are things that you could do if you want to do this for a fluxonium, but we also want to try out this so that we don't have to have this like extra tunable resonator. I mean, it's a way that allows you to have just like a normal resonator qubit, and then you could potentially operate it as like digitally, but you can also like do persistent current because you can do this projection.
But I guess the Northrop Grumman's solution to this was to insert this thing they call a quantum flux parametron between the qubit and and here, which is essentially a current amplifier. So in principle, you could do that with the fluxonium. I answered correctly.
Yeah, I mean it's still a challenge because even in this Northrop Grumman paper, if I remember correctly, the persistent current they have is 190 nanoamps. I read the paper recently.
Something like that, yeah.
And the currents that we have for the fluxonium are about like an order of magnitude lower. So maybe you can do it, but it's for sure trickier. Yeah.
Sure. Also, there is a patent. Yes, that's also a complicating factor. I agree with that, Paul. Get your legal team to work on that one. Well, we should probably conclude there because the coffee break is next. And so let's thank Victor once again.